All right, guys. In this video, I'm just doing some more kinetics practice problems that show up on the AP exam. So I just have some free response from the past couple of tests and some multiple choice problems from released AP past exams. And it's strictly just kind of the kinetics questions that I want to focus on here. Um, so it says Unit 7. That's just if you take AP Chemistry at West Springfield, our Unit 7 is when we do kinetics. If you follow the order of the course from College Board, then we're talking about Unit 5 stuff. I think that's when College Board does kinetics, is in their Unit 5. So it says, our Unit 7, it's still the same concepts. Right, so chemical kinetic questions, right? So we're talking about rate laws, differential rate laws, reactant orders, reaction mechanisms, how to speed up a reaction, that kind of thing. So I just want you to see the types of questions College Board likes to ask when it comes to kinetics, both on the free response and a few examples from multiple choice questions. Okay, so uh, first thing to understand is kinetics isn't a large portion of the AP exam. So there'll be a few questions on chemical kinetics, but there won't be that many. It's not worth that much of the overall exam. So what are we looking at? We're looking at like two, maybe three multiple choice questions. And if it's on the free response, if kinetics shows up on questions 1, 2, or 3, then it's probably just going to be a small part of the question. Maybe the question starts out predominantly thermodynamics, and then at some point there's a couple kinetics questions, and then maybe it goes to equilibrium or something like that. So um, if there is like one full free response question that is solely based around kinetics, it would have to be one of the last four free response questions, the shorter ones, the ones that are only worth 4 points. You're not going to, maybe kinetics might be worth 2 to 3 points on the free response in total out of the 46 points. And again, on the multiple choice, maybe two or three questions on kinetics on the multiple choice. So it's not that much. And um, but and a lot of it's pretty straightforward. So like if you just understand the basics of kinetics, our Unit 7, College Board's Unit 5, you should be able to answer the questions. There's not a lot of like trick questions for kinetics. There could be trickier questions every once in a while, but for the most part, they're pretty straightforward. Okay. It just might be, you're used to be given this to find that. And then now it's a question where you're given that. So you have to go back the other way. So you might be used to, seeing a question from, left to right, but this time you have to do right to left or something like that. But anyway, so we're going to start off with some free response, um, and then go into some multiple choice. And so you'll see some other things on here that I'm not discussing because it's just this is part of one of the free response questions from last year's AP exam, and then I think the year before as well. But like question D here is not a kinetics question. This is from our Unit 1, right? This is a structure question and that kind of thing. So for this question, right, they give us the reaction and they give us the initial rate data. So as soon as I see this, maybe I'm thinking, all right, I got to figure out each reactant order, right? So when I change this concentration, how does that affect the rate versus when I change this concentration, how does that affect the rate? The other thing I want to maybe look at is the units, especially the unit of time for the rate, because if they ask me about the units of K, which they do in this question here, I know that the time unit for K is going to be seconds. Like if this had been molarity per minute or something like that, then the time unit would be um, minutes instead of seconds. So that would be kind of one thing to, just kind of notice right off the bat. The other thing to notice is what rate you're given, right? This isn't, you might be given the rate of the overall reaction, or you might be given the rate of appearance or the rate of disappearance for a reactant or a product, right? So, like, but remember, if this thing that we're monitoring the rate, in this case, it's the rate of formation of this product. Since that coefficient is 1, that is the overall rate of the reaction. And so they don't ask this question, they don't ask this in this setup right here in this question, but one thing I might do is, okay, if I know the rate of the formation of this thing for trial 1, then if I want to know the rate of formation of this ion, all I have to do is take this and multiply it by 3. Or if I wanted this ion, take this and multiply it by 2. Or if they ask for the rate of disappearance for one of the reactants, then it would be the same number, because that has a coefficient of 1, that has a coefficient of 1, that has a coefficient of 1. So they're all 1-to-1 ratios. But they don't ask about that, but that's just one thing to kind of notice. Like, what rate were you given? The rate of formation of this product, or the rate of disappearance of this reactant, or the rate of the overall reaction? And if you have the rate of one thing and you're finding the rate of something else, all you have to do is multiply by your coefficient ratio, your mole ratio, to convert rate of one thing to rate of something else. And if they have the same coefficient, they would have the same rate of formation or disappearance, right? So on my key, that's what I noted. It said, notice it was the rate of formation of this thing. So multiply it by 3 to get the rate of formation of that. Multiply it by 2 to get the rate of formation of that. Just some kind of notes. Okay. All right. So the first question, they give us the rate law. So we're not determining the reactant orders because they tell us the rate law. So they're telling us that this is first order, and I3 minus is also first order in terms of reactant order. We have to explain why they're first order based on that, right? So we don't have to discover that they're first order based on the data, but we could, but we have to explain why the data shows that they're first order, okay? So remember, they're just asking about this reactant, right? So really the question is, why is this first order? But we can do it for both reactants just to show how it does. But remember, if you're taking the AP exam and they ask you just about that, only answer that. Don't waste your time answering the other thing, right? So remember, all we have to do, like if I want to find the reactant order of this thing, and I'm given this type of data, I would just do, this number divided by this number, okay? Find the two trials where this concentration changed, but this concentration stayed the same, and see what happened to the rate. And, sometimes you can do it without a calculator, sometimes you can't. So to be sure, you would just do, this divided by this. And then if you do this divided by this, and it comes out to be the same number, then that's first order, right? If the rate changed by the same factor that the concentration changed, then that's a first order reactant. And it is a first order reactant. So I'm guessing when I do this divided by this and this divided by this, I'm going to get the same number, right? So that's really all we have to do to prove it, right? So notice when I did the concentrations divided by each other, I got 2. And then when I did the rates divided by each other, it's not exactly 2, but 1.99, so it's 2. So that means changing the concentration did the same thing to the rate. How I changed the concentration, changed the rate the same exact way. That's a first order reactant, okay? So the same thing we would do with this one, but the two trials we would have to look at are trials 1 and trial 3, because that's the trials that we changed this amount, but we kept the other reactant the same, 1.2 and 1.2. So what I would do, and I like to do big number divided by small number when I'm doing this. So I'm not going to do this number divided by this number. I'm going to go ahead and do this number divided by that number, and then this number divided by that number. Now, again, understand what to anticipate. When I do this divided by that, and then I do this divided by that, if it's first order, it should be the same number, okay? Now, if I did this divided by that and it came out to be 2, but then I did this divided by that and it came out to be 4, which is 2 squared, that would be a sign that my reactant is second order. We know it's not second order because, again, they gave us the rate equation, but I'm just saying, if it was second order, then if I doubled the concentration, the rate would quadruple. It wouldn't also double. That would be a sign if it's first order, okay? If it quadruples when I double the concentration, that's a sign that it's second order, all right? So again, when I do the concentrations divided by each other, I get 2. And when I do the rates in the same trials divided by each other, I get 2. So the rate changed the same amount that the concentration changed. So it's a first order reactant. Okay. All right. So again, pretty quick, straightforward, easy questions. You just got to make sure, you kind of, you can jump to some conclusions by just different things you see. And then, read the question. And then a lot of times you've already answered the question because of the things you've already identified. All right. So the next question, it's just this one right here. Okay. So again, this was, so these were the only, so I guess 3 different questions that would be considered chemical kinetics on last year's free response portion of the test, right? So we had these 2 questions in one of the earlier questions on the exam. And then notice this is question number 7. And A and B are not kinetics questions. C is, right? Reaction mechanisms. Okay. And again, let's, as soon as I see I have a mechanism, and, we see equations kind of on top of each other all the time when we're thinking Hess's law, or maybe we're adding an oxidation and a reduction half reaction, right? So we see this, but remember when you're given like this, step 1, step 2, step 3, step 4, remember that's a reaction mechanism, right? So we have our overall reaction, and they're telling us this is the mechanism for the reaction. And as soon as I'm looking at a mechanism, remember, I'm looking a lot of times for, one of 2 things. I'm looking for intermediates, because if I have a multi-step mechanism, I'm going to have intermediates, or maybe a catalyst, right? So you don't always have a catalyst. It has to be the catalyzed reaction if it's a catalyst. But you will have intermediates. So just real quick, like the intermediate would be this thing, right? Because it is produced and then consumed. Notice it's not a part of the overall reaction, okay? And something in a reaction mechanism that is produced first and then later used as a reactant, then consumed later on, it cancels out on this diagonal, right? Going this way. That's an intermediate, okay? A catalyst is something that is used first, so it's a reactant first in the mechanism, but then it's produced later on. So notice a catalyst is not a part of the overall reaction because it cancels out when you add the 2 steps together, but it cancels out this way, right? So if anything cancels out on this diagonal in a reaction mechanism, that's a catalyst. When things cancel out this way, it's an intermediate. Okay. So like when I look at this, I know it's the catalyzed reaction because I do have a catalyst. Hydronium is a catalyst, okay, by definition of what a catalyst is in a mechanism. And this thing is an intermediate. They don't tell me how fast each step is, so I don't know which one is the rate determining step. Maybe I have to answer a question about that. But right, so I don't know which one is the faster step or which one's the slowest step. I don't know which one's the rate determining step, so I might not be able to figure out what the actual rate equation is for this reaction. But I do know that I do have a catalyst. It's a catalyzed mechanism, and hydronium is a catalyst. And I do know that this is an intermediate. Okay. And if we read the question, oh, I forgot. I didn't answer part 2 of this one. I'll come back to that. Sorry about that. So let's continue what we were doing. Crazy. All right. So notice that hydronium does cancel out. And if we read the question, it says the student claims that hydronium is a catalyst for the reaction. Okay. Yeah, I agree with the student. And then they ask you, do you agree or disagree? And justify based on the mechanism. So all we had to do is say, we agree, and hydronium is used and then produced within the mechanism. That's what defines a catalyst in terms of reaction mechanism, right? It lowers the activation energy. How? It provides a different mechanism. What's true about that mechanism? It has a lower activation energy, and it's used first and then produced within the mechanism. Okay, so that's really all we had to say there. Okay, sorry, let me go back up to the last one. Let's go back. Get your mind back to this one. So remember, we have the rate equation from this question, and now all they're asking is the units of K. We have to calculate the value of K, and we need the units of K. All right, so remember, we know the time unit for K is going to be seconds. So remember, for the rate constant, it's 1/seconds. But then there might be a molarity part to it, okay? So remember the shortcut for the units of K for any rate equation. The units are going to be 1/molarity raised to the reaction order minus 1, and then 1/time. And in this case, 1/seconds, right? So for this reaction, right, I can go back up here. The reaction order, remember, reaction order is the sum of the reactant orders. So the reaction order is 2, because 1 plus 1. So the reaction order is 2. So we're following our little shortcut for, for the units of K. It would be 1/molarity raised to the second power minus 2. So raised to the 2 minus 1. So molarity raised to the first power, and then also 1/seconds. So that would be the units of K. So if you run it like that, you can get credit. But remember, on multiple choice, usually they'll write units that look like this way, right? Remember, 1/molarity is really liters over moles. So another way to say that is liters times moles to the -1, which would be 1/moles, and then times seconds to the -1, which would be 1/seconds. Okay, so just, if it's free response, you can write it that way. But if it's multiple choice, the answer is probably going to be written like this for you. So make sure you can interpret that type of unit. All right. So, but how do we calculate the value of K? We have to take data from one of the trials. You can pick which trial you want. I usually just go with trial 1. We plug in our molarities into the rate law. We plug in the rate where it says rate into the rate law, and the only thing we don't know is K. And so that's all we do. So I took the data from trial 1, plugged it in, the rate here, the molarities here, they were raised to the first power because they were both first order. And so all we have to do is take the rate divided by that, and we get the value for the rate constant. But remember, whenever you have to calculate a rate constant on the AP exam, they will ask you for the units, and you won't get the point if you don't get the proper units, right? So again, this way or, this way. And the AP exam, there'll be at least one question, multiple choice or free response, where you will have to, and sometimes you don't even have to calculate what K is. You just have to know what the units for K will be. Okay. All right. So sorry I missed that one. All right. So again, that was the free response section for last year's AP chemistry exam, 2025. And there were only 3 prompts on the free response that dealt specifically with kinetics. Okay. So 3 points out of the 46 came from 8 College Boards Unit 5, our Unit 7. Okay. All right. Now, this is a free response question, but this is, I think, from the year before. I think this is the 2024 test. So here, these are kinetics questions. Like now, number 1 here is pretty easy. And, technically we learned this in our Unit 7 and College Board Unit 5, but it's something that we learn in Chemistry 1 as well. So it, like, understanding how to speed up a chemical reaction. So, if you have a solid and you want to make it react faster, you crush it up, right? So what happens to the surface area of the reactants when a student grinds the chunks into powder? It increases. Okay, that's it, right? So really you just say the surface area increases, right? Now, what will that do? That's going to speed up the rate of the reaction, and that's what we have to kind of talk about in part 2. All right. So again, why do you crush up a solid? Why do you cut it up into pieces? Why do you crush it up into a powder? To make it react faster. Okay. If the reaction is just it dissolving in water, break it up, crush it up, it'll react faster, right? So number 1, right? You break up a solid, you've increased the surface area. Now, what does that do? That increases the number of sites where collisions can occur, if you have more total collisions, you'll end up with more total effective collisions, and that means the reaction happens faster. Okay, so in part two, they're saying, will the reaction happen faster when they use the crushed up powder versus the chunks dissolving? And the answer is yes, it will be shorter. It will take less time for it to dissolve when it's crushed up into powder, because the increased surface area increases the number of chances for collisions. It increases the overall number of collisions that can occur per unit of time, and that increases how fast the reaction occurs per unit of time, right? More collisions is going to mean more effective collisions, and that means the reaction's happening faster. Okay, so it'll take less time for it to dissolve. All right, so that's again pretty straightforward. And if there was one more free response. Sorry, it's at the end of my packet here. Okay, so this was also from the 2024 exam. So from the 2024 exam, there were 4 prompts that were from chemical kinetics. So 4 total points out of the 46 that came from College Board Unit 5 or Unit 7. On the last year's AP exam, there were only 3 points total on the free response section. So maybe a couple more multiple choice questions on last year's multiple choice, and maybe like one less multiple choice question on kinetics on 2024's multiple choice. Okay. Now, remember, if you see concentration versus time, if that gives you a straight line, that's 0 order. If natural log of the concentration versus time gives you a straight line, that's first order. And if 1 over concentration versus time gives you a straight line, that's second order. So as soon as I see this, that the 1 over concentration versus time gave me a straight line with a constant slope, I know this reactant is second order. If this had been a straight line, then it would have been first order. And if this line was straight, then this line wouldn't be straight. Okay, so that's real easy, right? So as soon as I see these charts, natural log, not a straight line, 1 over is a straight line, I know I'm dealing with a second order reactant. Second order. Okay, right? Now, if you read the question, they tell us the rate law for it, and it is saying it's second order. And I'm guessing this question is about, how does the graphs tell me that it's second order? The rate law tells me it's second order, but how do the graphs prove it? Okay. And that's a real easy question. I'm going to have to scroll to the end here. We'll come back to the multiple choice. So again, 1 over gave me the straight line. I know it's second order automatically. I know it can't be first order because this graph wasn't a straight line. And again, by straight, I mean constant slope. And you could say the graph that shows 1 over concentration versus time gives us a constant slope. That means the reactant is second order, right? That's all we had to know, right? Now, for this one, they tell us the rate of disappearance of NO2 at a given point in time. And they say, okay, if that's the rate of disappearance for NO2, what's the rate of appearance for oxygen at that same moment in time? Well, all we have to do is a little stoichiometry, right? All we have to do is say, take the rate of NO2 and multiply it by 1 and divide it by 2, multiply it by the ratio, and that'll give us the rate of oxygen. So all we have to do is take the rate of NO2 that we're losing, multiply it by 1 over 2, and that'll give us the rate of formation or the rate of appearance of oxygen. And it would have the same units as the rate of disappearance for that reactant. Okay. If it had asked for the rate of appearance of this, it would be the same number because it's a 1-to-1 ratio. Okay. All right. So again, notice like the kinetics questions, right? If you just remember, like if it's 1 over, it's second order. If it's natural log, it's first order. If it's just concentration, it's 0th order. That's probably 80% of the kinetics questions that ask about the integrator rate laws are questions like that, right? So if you understand that, you're good for pretty much anything they'll throw at you. Now, they might throw a more challenging integrator rate law question at you, and we should be able to figure that out. But for the most part, this is what we're seeing. right? We got to be able to do this. If we can answer the easy stuff, right? And how long does it take me to answer this question? Not long at all, right? A lot of students get these questions wrong just because this was number 6 and it's the second to last question on the free response, and they just didn't make it that far because they spent too much time on other questions. Okay. All right. So now let's do some multiple choice practice, and I'll zoom in and out so you can see the question. And if you have to like pause the video and read the question, that's fine. But again, I kind of want you to see how Kinetics shows up on multiple choice as well. And see if I can zoom in here. Can I? Yeah. All right. All right. So I want you to see how it looks here. Okay. So here, this first question, right? This is just say, hey, anytime they're asking you what a catalyst does, right? They say catalase, catalyze, enzyme. We know those are catalysts, right? In chemistry, it's usually like, what's the purpose of a catalyst? And we know it's to speed up a reaction, but how does it do it? It lowers the activation energy. It provides a lower energy pathway. It provides a lower energy mechanism, all that good stuff. But a lot of times you're just looking for something that's saying it's lowering the activation energy, right? So we see that it's really asking us what a catalyst does, and we want to find something about the activation energy, okay? Right? If we look at B, it says binds temporarily to reactant molecules, and that's kind of what enzymes do, right? They take the two reactants and they orient them so that when they collide, it's the exact right orientation that's needed for an effective collision. Okay, and that's why the activation energy doesn't have to be so high, right? Because instead of relying on a lot more energy in the collision doesn't have to be that hard because they're lined up perfectly already, right? So, right, it's going to be B because it's lowering the activation energy, right? That's what we're looking for. All right, let me scroll up here, right? So again, right, we want to be efficient test takers. That's part of the game. We want to make sure we read every single multiple choice question in the 90 minutes that we have. And, so sometimes we need to take some time and actually read everything that's in there, but like catalyze, enzyme, lower activation energy, boom, I got it. All right. All right. Now, again, what did we say? Concentration versus time, natural log of concentration versus time, 1 over concentration versus time, right? If it's, right, what's the deal? If we make our 3 graphs, this on the y and time on the x, then this on the y and time on the x, then this on the y and time on the x. Whatever gives us the straight line with a constant slope, that's the one that tells us the reactant order. So if this gives us the straight line 0th order, if this gives us the straight line 1st order, if this gives us the straight line 2nd order, right? That's it. Okay. Now, how can we tell if it's going to constant slope, right? Do I have time to make graphs and stuff, right? No, but you can find the difference between here and here, and then the difference between here and here, and the difference between here and here. And as long as the intervals of time end up being the same, and in this case, 100 seconds, and then another 100 seconds, and then another 100 seconds, right? If this changes the same each time, that this changes the same each time, it's going to have a constant slope. The rise and run is not going to change. So if we do our math, this is increasing by 0.75 each time. If we do the differences here, we're going to know that we get different numbers each time. This one, we get different numbers. So these wouldn't have a constant slope. These would not produce a straight line. This would produce a straight line when I graph this versus time. So that means it's 2nd order. So the rate equation would have to show NO2 as 2nd order. Okay. Right. Another thing to understand is, remember, rate equations, you don't divide by stuff, right? Rate equations is just rate equals K, and then it's brackets all the reactants and then raised to their reactant orders, but we don't divide by products. That's the equilibrium constant. So if I know I'm looking for a rate law, like I can eliminate choice C and choice D if I have to guess. I know it can't be C and D. That's not what a rate equation looks like. All right. All right. Now, What we have to remember is if we're told something follows first order kinetics, that means the half-life is constant. The other thing it means is we can use this equation. Half-life equals 0.693 divided by K. This is on your formula sheet in the kinetics section. But you can only use this when it's first order kinetics. Lucky us, it's first order. They're telling us it's first order. Okay. Remember, radioactive decay is always first order. So if it's a nuclear decay half-life question, you can always use this equation. Nuclear decay is always first order kinetics. That's not what's going on here. It's just a decomposition reaction. It's not a nuclear decay reaction. Okay. But since it's first order kinetics, that means the half-life is always the same. And that means you can use this equation to calculate the half-life. Or if you know the half-life, like we know in this question, you could use it to calculate K. So that's what we're going to do. We plug in the half-life where it says T1 half. That's what half-life, that's the thing that means half-life. We plug in the 56 into here. And then we plug in the 56 days into the half-life, okay? And then we solve for K. Now, K comes out to be a value of 0.012. Maybe to make it more complicated, maybe they'll have the same value, but with the incorrect unit. Remember, K is always at least 1 over time. And for first order kinetics, since the reaction order is 1, the units of K will just be 1 over time. But the unit of time has to match the unit of time for the half-life. Since it was days, it would be 1 over days, or days to the -1 for the units of K. All right. All right, so when we move to this next one, we've seen this practice problem before in last unit, but I would just, again, how kind of thermodynamics and kinetics are going to tie into each other, especially on the AP exam, right? They love to give you a reaction where delta G is negative. So as soon as we see that, we know the reaction is thermodynamically favored. But then they give us a scenario where we know we have a thermodynamically favored reaction, but the reaction isn't happening. And you're usually asking, well, what is causing the reaction not to happen, even though it's thermodynamically favored? And whenever they're asking that type of question, the answer is usually because of a high activation energy of the reaction. So it's thermodynamically favored, but right now there's not enough energy for the activation energy of the reaction to be met, right? So really, we're just looking for anything that's talking about a high activation energy for this question. And if we look at choice C, the reaction has an extremely large activation energy due to the strong three-dimensional bonding among carbon atoms. You remember, unit 1, we always were talking about network covalent compounds like carbon and graphite and stuff, and they have strong network covalent bonds. So that's just kind of reaffirming that. So again, the answer is choice C in this case. All right. All right, so if we look at the next kind of grouping, here, notice we're given reaction mechanisms. And if we look at both mechanisms, the first step of each mechanism is the rate determining step, okay? Remember what has to be true about a mechanism? The steps have to add up to the overall reaction. All right, so these 3 steps have to add up to this equation. And for mechanism 2 to be a valid mechanism, those 4 steps would have to add up to the overall reaction. All right, so this question is just saying, hey, really which mechanism is consistent with what we're given? Or are they both sufficient, or are they both not sufficient mechanisms, right? Could they be possible? Could they not work? So one thing that could cancel one of these out is if they didn't add up to this equation. But if you do the math, they both add up to this reaction. So in terms of being possible mechanisms right now, they both could be possible mechanisms, right? But what else has to be true? The mechanism has to agree with the rate law. The rate law is telling us that this reactant is first order. And if we look at the rate determining step and any step above it, x squared in this mechanism shows up, or not x squared, x sub 2 shows up once. So this mechanism is showing it as first order. but this mechanism is also showing X sub 2 as first order. So both mechanisms fit the data. So the answer is C. Both mechanisms are consistent. All right. All right. So both add up and both show x squared as, or not x squared, I keep saying x squared, x2 as first order. Okay. So that's why they both fit. Okay. All right. So if we look at the next grouping of questions, really it's only number 32 in this set that, is kinetics. And again, it's just taking the rate of one thing and multiplying by the coefficients to get the rate of the other thing. So they give us the rate of appearance of oxygen. And again, remember, if it's a product, it's going to either be the rate of formation or maybe the rate of appearance, because those things are being formed as the reaction proceeds. And if they're asking about a rate of a reactant, it's going to be disappearance or maybe consumption, because those are being consumed as the reaction proceeds, right? So this is for oxygen. So all we have to do is take this number, multiply it by 2, the coefficient of permanganate, because that's the rate we want, and then divide it by 5, because that's the rate of, that's oxygen's coefficient. And it comes out to be this guy, D, 4 times 10 to the negative 4. Okay. So again, right, you would just take that times the mole ratio, right, times the coefficient ratio, and then you get that. Okay. All right, so that's pretty quick one. All right. Here, natural log versus time gave us a straight line. First order. B. That's it. That's all you have to do, right? That's all it is. If this had said 1 over the concentration of Z, then it's second order. If this had just said the concentration of Z, then it's 0 order, but that's it, right? As soon as I see that, as soon as I see it's the natural log graph that's giving me the straight line, that's first order kinetics, right? If this graph gives me a straight line, 0 order. If this graph gives me a straight line, first order. If this graph gives me a straight line, second order. Remember, when you graph concentration versus time data and you make these 3 different graphs, only one gives you a straight line. And the one that produces the straight line is the order. If it's this one, it's 0 order. If it's this one, it's first order. If it's this one, it's second order. All right. So I saw that graph that's asking me, what does that tell me about reactant Z? It's telling me reactant Z is first order. Okay. All right, here. All right. What should we notice right off the bat? All right. We got our potential energy diagram. I noticed that the forward reaction is endothermic. Why? Because it increased in potential energy. It increased in enthalpy. What is the delta H? It's positive 50 for the forward reaction. It would be negative 50 kilojoules for the reverse reaction, right? They give me 2 pathways. This is the uncatalyzed reaction, and the dashed line is the catalyzed reaction. What changed? We lowered the activation energy. That's what a catalyst does. So path 2 is the catalyst path. Path 1 is the not catalyst path. Okay? So all those conclusions we jump to right from just seeing that chart. Okay? So the first question is just asking about path 2, and we already answered it. It's the presence of the catalyst, right? That's what a catalyst does. Lowers the activation energy. Okay. And then 45 is more maybe of a unit 3 question, unit 6 question, thermodynamics, but exothermic. We know it's endothermic. Remember, that means energy is absorbed from where? It's coming from the surroundings into the system. So this is asking what the energy transfer is. We can cancel out C and D because we know it's not, we know the delta is not 100. The change is 50, right? The delta would be this this energy value minus this energy value, right? So the delta is 50. Okay. So it's not C or D, and it's the surroundings are losing energy. So heat isn't transferred to the surroundings. Heat is transferred from the surroundings. From the surroundings, where does it go? To the system, to the reaction. All right. So, and we know that because it was endothermic, right? If this line was lower, than this line, then that would be exothermic, and the answer would have been 50 kilojoules transferred to the surroundings. But since it was endothermic, that means 50 kilojoules of energy transferred from the surroundings. Okay. I don't like the way they worded that, from the surroundings, but that's the way they did it. So that's I would like to say heat's released, or heat's lost from the surroundings, or heat's absorbed by the system. Something, I don't know, but whatever. All right. This other one, I'll zoom in. Sorry you can't see it. But this one, if you can read this question, okay, this question is basically asking, it's a collision theory question. Remember, in order for a reaction to happen, the reactants have to collide, but just because they collide doesn't mean they are going to react. They have to collide with the right energy. We call that the activation energy, right? But just because they collide with the right energy doesn't mean it's going to react. It also has to have the correct orientation. So what this question is asking is, hey, we have a lot of collisions with sufficient energy. We have a lot of collisions that are meeting the activation energy of the reaction, but the reaction isn't happening that fast, right? Due to the number of collisions that have the right energy. And why is that? It's because they also have to have the correct orientation. So yes, a lot of those collisions have the right energy, but they don't have the right orientation. So they're not effective collisions, right? It's more than just the energy. It's also the orientation. So why isn't the reaction happening based on the number of collisions that have the right energy? Because it's about the correct orientation as well, right? So the two reactant particles must collide with a proper orientation in order to react. Okay. All right. So that's just going over some practice. Unit 7, College Board's Unit 5, just kinetics questions. This is how it shows up on multiple choice. This is how it shows up on free response most of the time. Take the test efficiently, you know, have those things in your mind. If it's this graph, it means 0th order. If it's that graph, it means first order. If it's this graph, it means second order. So all those things are important. As soon as you know something, one thing's true, what are all the other things that you know that must be true now about that reaction? Making those connections, that is very important. All right. Okay. So, all right, have a good one.